Guys, today we'll start with our chemistry course and we'll start with unit 1 and chapter 1, which talks about states of matter. So there are three states of matter. Actually this course will be consisting of IGCSE chemistry, IGCSE chemistry 9 to 1, and we'll cover whole book, and we'll have to cover GCSE also. So we'll start off. There are three states of matter: solid, liquid, and gas. And we'll start off with solid first. That solid are particles that are arranged in a regular pattern and are packed closely together. For example, in this picture we can see that particles are arranged in a perfect straight line and they are closely packed to each other, that they don't have spaces between. These in spaces are like just because of drawing, but they don't have space in between, and they are having fixed position. For example, that if we have a bottle or water bottle, the particles inside the water bottle are at a fixed position. It don't move around here and there, which keeps it in a proper state. And then we have the particles tend to vibrate at a fixed position when they gain kinetic energy. For example, there is a fire source here. We are providing heat. Alright, and this heat causes this particles in a solid to vibrate quickly, and because they vibrate because they are tightly packed and they are at a fixed position. If they were having some gaps in between them, they would be moving around because they have gained kinetic energy, but they don't have space in between them, so they do not move here and there. And then we have another point, that is that particles can't move around. Obviously when they are in fixed position they can't move around. And then we have the particles in a solid tend to have a strong force of attraction between themselves. So the forces of attraction between the particles in a between particles in a solid are very strong, which keeps the solid in a particular shape and a fixed shape. And then we have that there are no spaces between the particles of solid. These are just some spaces because of drawing, but in reality they don't have any space in between and there are no gaps in between them. So in summary we say that solids don't have any gaps in between them. They are at a fixed position and they don't move around, and they as they uh, as they gain kinetic energy they tend to vibrate at one place. So this is all about solid, and that also they have a regular pattern. There are no irregular patterns, which means that they are in a straight line. And then let's move to liquids are mostly same like solids, but there are some differences. That there's space between the particles. They are not like solids, the totally like solids. Gases are totally different, but liquid and solid there's some similarities like the looking, but there is an irregular pattern than the solid particle, and they can move. They are almost touching, means they don't have those big gaps like gases. So one first, that they move around and they are not in a fixed shape and they are irregular. And then second, we say that they are not mostly touching each other, which causes them to have a low force of attraction between them. They have some gaps in between them, some not tightly packed like solids, and that's the difference between them. And saying that they have an irregular pattern, they are not aligned in one line, and they are not letting like solid particles in phase of looking at this picture and this picture, that they irregular and they have some gaps between them, and they are less dense than solid because they have some gaps between the particles. And the force of attraction, as I say, is weaker than the force of attraction between the particles in a solid because they have gaps in between them. And the particles, when they gain kinetic energy, they tend to move around. That is how boiling and evaporation happens, as I'll explain it later. But this is how it happens, that when it gain kinetic energy, this particle starts to move randomly in a container, bounces off another way and moves around. And then we have gases. Gases, they are also form an irregular pattern, and their gases are way apart from each other, and they have huge space in between them, and they have the lowest force of attraction. You can see in the picture they have huge gaps, even I can draw it between them, and this causes the force of attraction to become very weak. And then we have that when they gain kinetic energy, they tend to move around as liquid particles. Even the force of attraction is so weak that they can move around in the whole container. So there are three states of matter: solid, liquid, and gas. And solid, they are tightly packed and they are in regular pattern, and they vibrate. Sorry, they vibrate at a fixed position, and they have the highest density, and they have strong force of attraction. Liquids, they are irregular in pattern, and they have small gaps between their particle. When they gain kinetic energy, the particles tend to move around, and they are less dense. And then we have gases, which are that they're irregular in pattern, and the gases are far apart from each other, means they have huge spaces which allows them to move here and there. And then it also means that they move around when they gain kinetic energy, and the low force of attraction allows them to move around. Then we have melting and freezing. So melting process, where is a process where solid turns into a liquid. The heat energy provided causes the particles in the solid to vibrate very quickly, so quickly that they which causes the force of attraction to get weakened in the solid, which causes it to become a liquid because of the force of attraction being weakened. For example, this is a solid. Alright, there are some particles in it which are tightly packed. I provide heat here. This heat causes the force of attraction to become weakened. The forces of attraction become weakened when this heat is provided, and when the heat is provided, the particle would vibrate at its own position. All the particles will vibrate. As they would vibrate, the forces of attraction will start to weaken, it will start to decline. The power or the force would reduce, which would cause them to move apart and become a liquid. The forces of attraction will become so weakened that they would become like this, that there are little gaps in between them. So when energy is put in, they melt because they vibrate at one position, and they weaken their force of attraction, and they turn into a liquid. And then in freezing is where the kinetic energy of the liquid particle is lowered, which causes the particle to move slowly. Eventually they come close to each other and cause them to gather up and turn into a liquid. In the solid, sorry, this is wrong, into a solid. So when energy is taken out, or when we cool the liquid particle, the liquid particles tend to slow down, and they slow down so much that they come closer to each other. When they come closer to each other, the forces of attraction tends to increase between the particles, which causes them to turn into solid again. And then we have boiling, condensing, and evaporation. So boiling, condensing, they both work in the same method, and this work in the same sense of melting and freezing, that when we provide heat, the particles tend to move faster, and and the force of attraction weakens. And the same happens for the condensing, that when when they are cooled, they slow down and they become liquid. But in boiling and evaporation, there's a difference. Evaporation is another process, and boiling is another process. So in condensing, we say that the gas particle come close to each other, and they eventually turn into a liquid. So these boiling and condensing are more likely same with melting and freezing, and they're also same with sublimation and deposition. So we'll talk about boiling and evaporation. Alright, so boil is, or it happens at a particular temperature. For example, for liquids, for water it happens at 100 Celsius, which is known as boiling point. As I have written here, boiling point, and it happens at a known temperature. It happens at a known temperature, and at a known temperature, just like water 100 Celsius, the particles tend to move away from each other. At a particular temperature, all the particles are moving away from each other and they turn into gas. That is what boiling is. But in evaporation can happen at any temperature. For example, these are some particles. Alright, just imagine that we are on a road and a liquid is spilled on the road. Alright, there's a road. I just think these some liquid particles, and the temperature on that day is 35 Celsius. This is an imaginative scenario, and then some of these particles have a kinetic energy, or which should be said that the kinetic energy increases at this temperature. So these four of these particles have the kinetic energy risen by because of this temperature, and it has caused them to move here around, which causes them to become gas. So these four particles have turned into gas, but these particles are still liquid. So evaporation happens at any temperature. It can be on 20 Celsius, it can be on 40, it can be 60, 80, 30, 45, it can be any temperature Celsius. But it depends on each liquid particle. So it requires any temperature, any liquid particle requires its own temperature to reach that kinetic energy to escape the surface of the liquid. So evaporation and boiling are two different things, and these two definitions will help you to understand it. What I said in simpler words, these are written as I explained with a scenario. And then we have sublimation and deposition, which works same as in the sense of melting, freezing, boiling, and condensing. The sublimation turns a solid directly to a gas, which we have to provide with tons of energy, and deposition is where gas turns to a solid. So this happens with gases such as oxygen and carbon. So then we have a small topic that working out the physical state is not working out, and then we have to work out the physical state. So for example, this example, alright, then we have to find oxygen at a state when it is as minus 200. When it is at minus 200, so we have to find the temperature, the physical state. So we would say that it boils at minus 180 something, give or take, and at minus 210 it melts. So it boils at minus 180, so it means that it has turned into a gas after the temperature. And in between melting and boiling, it is a liquid. So it is a liquid between minus 210 or 20 and minus 180, and after minus 180, for example, I'm saying it is an gas, and before minus 220 it is a solid. At absolute zero it is a solid. It happens for many things such as bromine also. Between melting, remember, between melting and boiling point, the physical state is always liquid, and after boiling point it is always gas, and before melting point it is always solid. Before melting point, I'll just type it will make it easier. is a simpler words to say that before melting point the physical state is solid, whereas in between melting and boiling point the physical state is liquid, and after boiling point after boiling point it is gas. So this is a simpler example or simpler way to withdraw our conclusion about this. Just remember these things. It's a simpler thing to understand. And then we have diffusion. So diffusion, I explained it in biology, and I'll explain again. The diffusion is spreading out of particles from where they are at a higher concentration region. There are lots of them in a certain volume to where they are at a lower concentration. There are fewer of them in a certain volume. So this the chemistry definition. Then we have an example through an experiment, which is a short experiment that which is between ammonia solution, concentrated ammonia solution, concentrated hydrochloric acid. The white ring is formed at near to hydrochloric acid because the diffusion allows them to reach there. First of all is that, and that in the same period of time the hydrochloric acid travels less time than travels less distance than ammonia solution, because ammonia solution is lighter and is quicker than hydrochloric acid, which causes the reaction to take place closer to hydrochloric acid, which interprets that ammonia solution particles are lighter and they are faster. And this is a small example of diffusion in a small experiment also. And then we have when a solid dissolves in a liquid substance that dissolves is called the solute, and the liquid which is dissolved in is called the solvent, and the liquid form is a solution. So this is a simple thing that I have a beaker and this is sodium chloride, and we put sodium chloride into the water, and this is the solvent and this is a solute. So it's a simple example. And then we have solubility. Solubility of a solid in a solvent at a particular temperature is usually defined as a mass of solute which must dissolve in 100 grams of solvent at that temperature to form a saturated solution. In other words, it is the maximum mass of solute that dissolves in 100 grams of solvent at a particular temperature. So this a definition. There's nothing to explain. This is a simple thing. You just memorize this. And then we have saturated solution, which contains as much dissolved solid as possible at a particular temperature. So it means that water has reacted completely with a solution, or any liquid has completely reacted with the solute, which means that it is completely dissolved and there's nothing else, or there's no more liquid particles to react with. So when we insert or add another solute particle, so it remains undissolved, it sinks at the below of the beaker. So this is what saturated solution is. And then we have completed our first chapter. We didn't talk about solubility curve because we'll talk it about in experiments, which is another playlist which I'll make after this unit being finished. So we'll start with our chapter 2. Chapter 2 is about elements and compounds and all those stuff. So elements are substances that can be split into anything simpler by chemical means. An element contains only one type of atom. For example, oxygen gas, it has only one type of atom. That is very simple example. And then compounds are formed when two or more elements chemically combine, or in the sense of through a reaction they combine in a fixed proportion. They don't have high, don't have low, they are in a fixed proportion, which is, for example, water. They have two hydrogen atom and one oxygen atom. So that's one example. And then we have mixture. And then we have mixture where substances are mixed together and no chemical reaction occurs. It can be with elements and compounds which are not chemically combined together. It can be formed in various components, and it can be formed in any proportion. A mixture of elements such as hydrogen, nitrogen and oxygen together. And then there are physical separation methods. Electrolysis is something we'll learn that in chapter 10, and by using a magnet. It can be like we have a mixture here, iron fillings, and we have sand. This thing is sand. So we can separate this by using a magnet, which will allow us to differentiate iron fillings from the sand particles. There's one example for using a magnet. And then we have hand picking method, where we take out big lumps of elements or compounds, form a mixture which is smaller, and will allow us to separate us compounds and elements from each other. And then we have sieving. Sieving is a method where we sieve the materials we want to and separate them according to their sizes if they are unable to be hand picked. And then boiling and freezing point. Every material, every compound, every element has a different boiling and freezing point, which allows us to find out and differentiate elements and compounds in between them, or their form in between. And then we'll talk about the separation methods which are more frequently used by people to separate mixtures. So first of all, we'll talk about filtration. Filtration can be used to separate a solid from a liquid. The substance left in the filter paper is called a residue, and the liquid that comes through is called the filtrate. So first we add a funnel to a beaker, and then we add a filter paper on it, and then we pass a solution with sand and water. And sand is something which cannot go through filter paper and stays on top of the filter paper, and the water passes through the filter paper and goes into a beaker. So the water is separated from the sand, and this is known as filtration, and the sand is known as a residue, and the water is known as a filtrate. You have to remember these names and memorize these names and understand them. And then we have crystallization. Crystallization can be used to separate a solute from a solution. The solution is heated in an evaporating basin to boil off some of the water until an almost saturated solution is formed. Saturated solution, as I explained before. And then after heating it, we can test it by dipping a glass oil into solution, seeing if crystals form quickly on the surface when it's removed. And the Bunsen burner is then turned off, and the crystals allowed to form as more water evaporates and the solution cools. The crystals can now be removed from the mixture by filtration. So we heat the solution, sodium chloride solution for example, and then we remove water from it, and it eventually becomes a saturated solution, which then we leave it to cool down, and then it turns into a crystal which is supposedly having some of water. Then we filtrate it until we find a clear crystal of sodium chloride. So that is how we separate a solute from a solution. And then we have simple distillation. That simple distillation can be used to separate the components of a solution. Although we can use crystallization, but we can also collect water by using simple distillation. Is seen by water is boiled and condensed back in the condenser, and the salt remains in the flask. When we boil this, the sodium chloride remains here, and the water moves through here and goes through from here also, and then it is collected here as it is condensed. So it is almost same like crystallization, but as an added feature that it can collect pure water. And then we have fractional distillation, where we can use it to separate a mixture of liquids such as ethanol or alcohol and water. Ethanol and water are completely miscible with each other, means they don't mix with each other, and that we can mix them in any proportion we want, and they form two single layers. And then we can separate them by using the boiling point at our advantage. So 100 Celsius is waters and 78 Celsius is ethanols. So when we boil them, when we reach 78 Celsius here, the ethanol would go through the fractionating column and would go through the condenser and would be found as almost pure alcohol, like 99-96%, almost in between them, give or take. And we'll have water here separated, and we'll have here ethanol separated. So this is known as fractional distillation. And then we have chromatography. Paper chromatography requires many things to be noted. Put a lid, because it is important, on the beaker so that the atmosphere becomes saturated with the solvent. This is stop evaporation of the solvent from the surface of the paper. So if the solvent is evaporated, then no chromatography or no paper chromatography experiment happens. And then we have to suspend the chromatography paper in a beaker that contains a small amount of solvent, so that the bottom of the paper goes into solvent. It is important that the solvent is below the pencil line, so that the inks colorings don't dissolve in the. This is an important point, that if we put the chromatography paper into the solvent, we have to take care of it so it doesn't dissolves the ink in it itself. And we have to take care of another point. I will just make it here: pencil line base, not a pen base. That is because if we make a pen base, the line, actually here the pencil line, if it is a pen, it will dissolve in the solvent, and there won't be any chromatography being taken place. So we have to take care of that by making it using by a pencil to do chromatography. And then we have retardation factor, which is stands as RF. Distance moved by a spot from the pencil line, or distance moved by the solvent front from the pencil line. And then we have to take care that this experiment will each time we do a chromatography experiment, the solvent and the spots will move differently distance along the paper. And this means we can't just report the distance moved by a particular spot, so we have to work out a ratio which is known as RF, and the pencil should be also noted. And then we have to take care of this calculation. We have to measure the distance moved by a spot. For example, this is the distance from the pencil line, and we have to put this term as x over the distance between pencil line and the solvent front as y. So there is your example, and this is how you do RF. You use it by finding a ruler and you will find it in the sense of centimeters, and there is no unit for it. That's the main thing. There is no unit for it. And this is all about chapter 2, and there is nothing else in chapter 2 to left. So we'll talk about chapter 3 and chapter 4 in our next video. So like my channel and like my videos and subscribe.